In real-world applications, tables can get very large in size. For example, the daily average number of trades executed on the New York Stock Exchange is roughly 2 billion. Manufacturing and IoT use cases can have much larger data volumes, with an IoT sensor having as many as 100,000 events per second. Q and KDB offer a number of different methods to store tables, which allows for efficient storage and querying, even over many days or years of high data volumes. For tables which can fit on one disk, there are 3 ways this can be stored: in a flat file, as a splayed table, or as a partitioned table. Flat file tables are when we save a KDB Plus table on disk entirely in one file. Tables can be serialized into well-known file types like CSV or other, but commonly the default serialization method is used to persist tables into a file with no type extension. When these tables are being read in from disk, they're fully loaded into memory. As a result, these tables should be small enough in memory footprint to be operated upon in RAM. It must be noted, however, that when working with tables in memory, if the process dies, then the table and any modifications made to it are also lost. So the general rule of thumb for a table size of a flat file table is anything up to a few million rows. When tables are too large to fit into memory, we can break it into pieces and save each column individually under a directory which is taken as the table name. This is called splaying a table. Splayed tables are particular in their on-disk structure. Inside the table directory, each column is saved in a separate file under the same name as the column name, and contains a serialized list of the values in that column. There's also a .d file, which is a KDB Plus binary file containing the order of the columns in the table. This resolves 2 main issues which are encountered when saving a table as a flat file. The first being that the flat file table must fit into memory, and the second being that operations on flat files can be slow due to it being reloaded in its entirety into memory each time. As a splayed table is essentially a directory of column files, this structure can be leveraged to increase the efficiency of analytics. With splayed tables, columns are loaded into memory on demand, thus increasing the performance of queries on this table. The general guidance for using splayed tables is anything from a few million rows up to 100 million rows. For anything over 100 million rows, partition tables are advised. As implied by the name, a partition table is structured as a series of partitions, each containing a splayed table of the data in the table as a whole relating to that particular partition. Tables can only be partitioned on values with a date, month, year, or a long KDB Plus type. When tables are saved under a partition, they inherit an extra column whose values correspond to the partition's value. So in this example, our table will have 4 columns: col 1, col 2, col 3, and partition 1. Splitting the table like this is usually done when there's a large amount of data associated with a given split, like storing the data for each day in a new partition. For example, if we have a table with 100 million rows across 10 unique dates, we might partition this table on date so that we can have 10 partitions and approximately 10 million rows in the splayed table in each partition. Queries on partition tables are usually executed on a limited set of partitions so that only those partitions specified are accessed. As a result, when querying a partition table, it is important to include the partition column as the first constraint to filter on. This speeds up queries as KDB Plus and Q only have to search through the specified partitions needed for the query. One thing to note here is that if your table contains a symbol type column, there's an additional step called enumeration which needs to be performed before the table can be persisted to disk as a splayed or partitioned table. When it comes to categorical data, users have 2 choices of data type to use: strings or symbols. Strings are easier to manipulate and are cheaper to store, but they're slower to query than symbols. Enumerations are a way to ease the storage burden of symbols by associating a data set with the set of its distinct values. For example, if we have a list of fruit as follows and extract the unique values from this, we can then use the index of this distinct list to associate a number with each value. This positional index can help to transform the original list of categorical values to the list of integers. And this is how enumeration works, and allows us to store the categorical list as a numeric list for cheaper storage, and use the distinct list to translate these numeric values back to categorical. When the column is queried, the distinct categorical list is indexed using the numeric values to retrieve the original list. This distinct categorical list is stored in what's known in KDB Plus as a SIM file and is central to all KDB Plus systems. The general rule of thumb for choosing between the string and symbol type is that symbols are used when the categorical values are highly repetitive and strings are used where the data is highly variable. So for tables that are too large to be stored on disk, segmented tables should be used. This involves storing data partitions in multiple locations outside of the root directory, with each location known as a segment. This is an extension of the partition table discussed previously, whereby each segment will house some number of data partitions. With this structure, KDB Plus can access and retrieve large amounts of data across segments in parallel. The only items that will remain in the root directory are any flat or splayed reference tables, the SIM file for increased storage efficiency for symbol columns, and a par.txt file. Each line in this par.txt file will give the location of each segment so that Q knows where to find all of the data. In order to get the most benefit from data segmentation, data partitions should be distributed evenly across segments, or consideration should be taken to common query patterns. Three main reasons why tables are segmented. The first is storage capacity. When dealing with databases in the order of petabytes, it can be necessary to split tables across many different storage devices, as it may not fit on one disk. There's also performance gains. When data is being retrieved from a given disk, the read and write performance is limited by the I/O capacity of the disk itself. So having different partitions on different disks can distribute the intensive queries across multiple disks, significantly reducing the overhead due to I/O. There can also be cost benefits. Often due to inherent recency bias, more recent data is accessed frequently, while older data is accessed far less so. As a result, it can be wise that expensive high-performance disks are used for the recent data, while the older, less accessed data is offloaded onto cheap storage disks. So those are the four ways that data can be saved on disk in KDB+. Each method has its own drawbacks and benefits, depending on the size of the data and the analytic requirements for it. But I hope that this video gives you a good overview of saving data on disk with Q and in KDB+. Thanks for watching.